Okay. There we go. All right. Oops. Let me just mute my phone and we'll get going. All right, welcome to the last of our presentations for the semester. Wow. Who would have thought that we'd be here now under these conditions? So I will be here this afternoon. After I get off of this, I'm going to go grab some lunch at the department office. They're having a little picnic kind of thing. And then I'll be back in the lab no later than 1. And I'll just be here all afternoon. Remember, those of you in lab, if you've got late labs, today's the deadline. You know, you got to get them in today. I won't count them. They'll count as a 0 if they don't get in today. So let's share the screen. And so we're going to finish up the course by talking a bit about ecological processes that go on at the very large scale, the global scale, and how they affect small scale ecological processes and kind of vice versa. So, oops, I gotta find my, there we go, slideshow. Come on. There we go. All right, let's move this back. All right, so the first thing we're going to talk about is the El Nino Southern Oscillation, which is a really great example of large-scale climate variability that affects small-scale processes at the local or even regional level. We'll then talk about the greenhouse effect, which is the cause of many of our problems today. And it arises directly from the accumulation of carbon in the atmosphere that we saw last time. You will remember that half of all carbon that's ever been emitted by the human species has been emitted in the last 30 years. So that's kind of a big deal. Then we will kind of turn it around and look at how humans, with their relatively small scale activities, affect the global processes. First, we'll give you a kind of a flow chart to show you how human processes directly affect or indirectly affect several things that we're interested in, like global biodiversity and climate. And then we'll drill down on 3 topics. We'll look at land use patterns. We'll look at nitrogen enrichment in the environment. And we'll look at greenhouse gases, okay, and talk about how they then sort of scale up in their effects to have global effects. We'll end this by talking about whether our somewhat desperate situation, people, have a lot of anxiety about this, but can we reverse our effects? And we'll give you an example of one global problem, which was really quite serious, that we have reversed, and talk about the timescale that we have available to reverse other things that we are doing. So first, let's talk about large-scale climate variables and how they affect small-scale processes. And we'll start with the El Nino Southern Oscillation. And I guess I got to go down here and do this. So there. Okay. So the El Nino Southern Oscillation is produced by the fluctuation of barometric pressure across the Pacific Ocean. Okay, and if there's low pressure, that means that air is rising. If there's high pressure, it means air is sinking. So what we've got here is high barometric pressure near Peru on the eastern side of the Pacific Ocean, and this is the Southern Oscillation Index. When it's positive, we have high pressure near Peru, sinking air, right? And that means that rising air is over by Australia. The warmest rising air on the face of the Earth, in fact, is in this tropical Pacific Ocean area. So when the oscillation index is positive, we have cold sinking air by Peru. And of course, that produces a desert, right? Because as it sinks, it warms adiabatically and sucks all the moisture from the surrounding environment. That's why Peru and Chile have coastal deserts. So when the index is positive, we have a high temperature, a high adiabatic heating of this sinking air near Peru. When the Southern Oscillation Index is below 0, when it's negative, it means we have rising air off the coast of Peru. And what that means is that the area of warmest rising air that can absorb the most moisture and produce the most rainfall is off of Peru suddenly. And so normally, or it's actually not normal, but we think of it as mostly being off the coast of Australia, in the region of New Guinea and Indonesia, all the way on the western side of the Pacific Ocean. But when this value is negative, that rising column of air that produces the heaviest rains really on Earth consistently is off of Peru. So as this swings from positive to negative, the column of rising air in the Pacific that produces the highest amount of rain swings back and forth from Indonesia to Peru, Indonesia to Peru. So this is indicative of the El Nino. The El Nino is the event that generally starts in late fall or early winter. Hence, it corresponds with the arrival of the Christ child. We call it El Nino for that reason. The Latin cultures of South America gave it that name. But it is characterized by warm temperatures, high rainfall, and a failure of the currents, a failure of the fisheries, because the rising air then prevents offshore flow towards along the equator from east to west towards Indonesia. So The barometric pressure is the index of El Nino or La Nina. These are La Nina conditions. These are El Nino conditions. In La Nina conditions, the rainfall is in Australia and Indonesia. In El Nino conditions, it's in Chile and Peru. Okay, what that means is that you got warm water here off Chile and Peru. Here you got cold water off Chile and Peru. This is the water that feeds the fisheries. This is the water that inhibits upwelling with nutrients and the replacement of water with cold Antarctic water that's rich in nutrients. So there's nothing for the fish to eat. They failed. All the birds die. Now, here's what it looks like from space. Okay, and during El Nino, you got warm water here. And look, the entire mid to northern coast of South America is bathed by relatively warm water. So the rising air here is generated by this big pool of hot water. And that makes a lot of rainfall in this part of South America. La Nina is typified by this kind of Antarctic current reaching up off the coast of South America, making it cold here and inhibiting the rising of air and the heavy rainfall. Instead, you see that what happens is that the current comes up from the pole and gradually gets warmed by the sun and then kind of moves off towards Indonesia. So this is typical circulation that we expect in an ocean gyre. In an El Nino, that circulation just comes to a kind of a dead stop. Okay, and warm water piles up here. Over here, the cold water infiltrates all along the coast, and that brings nutrients, although it also brings arid conditions. So here's a diagram again to reinforce this. During a La Nina, that area of maximum heating of the ocean surface and the maximum hot water that's producing the maximum rising air and maximum rainfall moves over towards Indonesia. During an El Nino, it moves towards South America. Okay. Now, as a result of this, this is not limited to the Pacific Ocean. This causes then changes in the location of all of climatic events throughout the world. It shifts every major climatic prevailing condition 4,000 to 5,000 kilometers from east to west. So when you have El Nino conditions, you have dry conditions in North America, dry conditions in Europe. I'm sorry, these are wet conditions. These are wet conditions, and these are dry conditions. Now, normally this rainfall would occur somewhere between 3,000 to 5,000 kilometers further east or west. So this rainfall would be occurring off the coast of Canada. This rainfall would be occurring near Hawaii. The dry conditions here that you see would be occurring also much further west. So this drought in the Sahel that is caused by El Nino would normally be dry conditions somewhere in the central Atlantic, very near the Windward Islands. Dry conditions here would be entirely in the Pacific Ocean, far, far to the west. Okay, drought here in Austronesia, kind of Australia and Indonesia, would be found in the central Indian Ocean where it's not doing a whole lot of damage. Okay, but these patterns shift from west in La Nina to east in El Nino. So it's a global phenomenon. It is not a local thing confined to the tropical Pacific. So areas of wet weather and dry weather alternate then, depending on whether you're in an El Nino or a La Nina condition. Remember, La Nina, Latin cultures, appears around Christmas. They named it after the Christ child. It's the rainfall and hot water and collapse of fisheries. La Nina is the what used to be thought of as normal conditions. That area of hot water goes much further towards Indonesia. Well, here is how El Nino affects the trophic structure of the Great Salt Lake in Utah. So here's the El Nino of 1982-83. Okay, and here's what happened as a result of this. So they had exceptionally high rainfall in Utah that year. By the way, they had drought in Costa Rica that year, and I almost was kicked out of graduate school because my dissertation failed. My dissertation project failed to get any data because it was a drought and I couldn't get any data. But in Utah, the opposite happened. They had tons of rainfall. So the salinity dropped drastically. Okay. And then in 84, it went back up again when the rainfall went away. So the salinity dropped. As a result of that, predatory bugs, which normally cannot tolerate salty conditions, salt kills them. But the salt was so reduced that the predators could move into this area of the lake. And as a result, the predatory bugs ate all the zooplankton. Okay, and so here's the normal density of, say, grazers. And Artemia is the most common one. And here you see it's really high when there's lots of salinity and high when there's lots of salinity, and it's really reduced because these bugs are eating them. Okay, so because then the grazers have been eaten, what happens? Well, all right, this is then a top-down cascade. Predators eat the grazers go away. What happens to the plants? Algae bloom. Phytoplankton bloomed and the Great Salt Lake turned green. So this global event has really profound local effects. High rainfall in El Nino caused a change in the trophic structure of the Great Salt Lake, causing an algal bloom that was smellable all the way in Salt Lake City, much to the dismay of the people living there. As that plankton rotted, it was a bad scene. Okay, now let's give you another example then of how these global effects have local impacts. So here, once again, the El Nino of 1982-83. Why are we talking about this one? Because it was the strongest ever recorded. So its effects were easy to see. So here's the number of red kangaroos in Australia. And you can see that in 78, there were about 1 million. And up through 1980, there's, not a whole lot difference. But then you get a spike in 82 as the El Nino comes in. Okay, and so this is rainfall induced. But then when the El Nino takes effect, what happens to the rainfall that's normally in Australia and Indonesia? It goes 4,000, 5,000 kilometers east to Peru. So now there's a drought. And here you go. The peak productivity of kangaroos that was produced by La Nina conditions here and steady rainfall crashed. Okay, so we had a huge crash among the red kangaroos. And it started to recover when the El Nino went away. Okay. But it didn't really recover until a really strong La Nina condition developed in Australia with lots of rainfall and produced lots of grass, enabling the population to increase again. So the increases are due to rainfall from La Nina. This initial increase here was 4 years of steady La Nina conditions, lots of rainfall. Then El Nino comes in and you start to get drought and the population starts to crash for lack of grass. And then it recovers when La Nina brings the rains back. So we're talking about global events, but they have massive local consequences for communities and ecosystems. Now, that's El Nino and La Nina. Let's talk about our friend, the greenhouse effect, which is giving us lots of problems right now. So it's important to understand that the Earth is inhabitable only because there is a natural greenhouse effect. If we didn't have a greenhouse effect, the Earth would be completely uninhabitable. There would be no life. The temperature on the sun-facing side of the Earth would be several hundred degrees, and the temperature on the side facing away from the sun would be near absolute zero. And those are the conditions that you find on lots of planets in the solar system. So the way that the greenhouse effect maintains moderate temperatures is by trapping solar heat. So here's solar radiation that's coming in from the sun. And so this is the width. The width indicates the total amount of radiation that arrives at Earth. Okay, so some of that is reflected back out into space by clouds. Some of it hits the Earth's surface and maybe hits something with high albedo like ice and is reflected back. Some of it's absorbed by clouds, by the atmosphere, warming the atmosphere, and then some of it is absorbed by the Earth's surface. So here's the energy budget of solar radiation from the sun. Some is reflected by the atmosphere, some reflected by high albedo surfaces on Earth, some absorbed by the atmosphere, some absorbed by the Earth. Forests and dark areas on Earth absorb the most. Now, remember that heat can be re-radiated. And when the solar facing side of the Earth turns away for night, the atmosphere then cools. It's cooling because it's losing heat to space. Okay, and as a result, then the atmosphere is cooler than the Earth's surface. And the Earth's surface then re-radiates heat to the atmosphere, and then some of the atmosphere re-radiates that heat to outer space. But some of that radiated heat is absorbed by clouds and then re-radiated back to the surface of the Earth. So the clouds become warmer than the Earth's surface, they radiate heat back to the Earth's surface. So that prevents the Earth's surface from cooling to absolute zero. It keeps it at a reasonable temperature. That is the greenhouse effect. Atmospheric gases absorbing heat and then re-radiating it to a cooler Earth's surface to maintain the Earth's surface temperature much, much higher than would be possible if we didn't have an atmosphere. So it's crucial that we have a greenhouse effect. There would be no life on Earth without a greenhouse effect. However, we have altered the greenhouse effect pretty dramatically. Okay, and the way we've altered it is that we've altered the concentrations of greenhouse gases, the gases that are responsible for trapping and re-radiating solar energy or heat energy from the surface of the Earth. So here is a list of the major contributors to greenhouse gas, and water, carbon dioxide, methane, ozone, nitrous oxide, CFCs. Okay, so here's the concentration in the atmosphere. Okay, and see, ozone is negligible. It's too small to measure. These three are too small to measure. Carbon dioxide is by far the most important greenhouse gas. Now, water vapor is estimated to contribute over half of the important greenhouse effect naturally. And that's because there's a fair amount of water in the atmosphere. Now, it doesn't build up in the atmosphere to any great extent because, of course, rain. If you get too much water vapor in the atmosphere, it simply condenses and falls at rain. So there's a low level of water vapor in the atmosphere constantly. It doesn't build up, but that low level of water vapor is responsible probably for about half of the greenhouse effect. It only lasts in the atmosphere about 9 days total. So if you evaporate water from a cornfield in Iowa, it'll stay up there floating around in Iowa. It'll maybe travel 20 miles to Illinois, and then it'll fall out 9 days later. Here's what happens with CO2 though. Okay, it's more concentrated. It's responsible for as much as a quarter of the total greenhouse effect. And the problem is it lasts many years in the atmosphere. So you put carbon in the atmosphere and it will build up for decades and it won't be absorbed by plants very readily. For all of the photosynthesis that goes on, carbon dioxide stays in the atmosphere a very long time. Okay. Methane is responsible for somewhere between 5 and 10% of the total greenhouse effect. It's more than 400 times more powerful at absorbing and re-radiating heat than carbon dioxide. So, hey, this is a huge concern, and it lasts for 12 years. Water vapor is not a worry for us because it just falls out as rain immediately. And there are people who try to argue, well, carbon is not the problem because water contributes more to the greenhouse effect. Yeah, but it doesn't build up. It bleeds out in 9 days. Water vapor doesn't stay in the atmosphere. Carbon dioxide does, methane does. Ozone has a relatively small concentration, but it's a powerful greenhouse gas, and it lasts on the order of days, fortunately for us. Nitrous oxide is also quite powerful relative to CO2. It absorbs and re-radiates 300 times more heat than carbon dioxide does, and it lasts for like over 100 years. Right, so you can see that there's a lot of gases that last a long time in the atmosphere that don't contribute quite as much as water vapor to the greenhouse effect, but because they don't go away, if they build up in the atmosphere, you're going to build up very rapidly an increased absorption and re-radiation of heat to the Earth's surface. One of the real interesting culprit is chlorofluorocarbons, which used to be used in refrigerants. They are at least 5,000 times more efficient at absorbing and re-radiating heat than carbon dioxide. And look, they last thousands of years in the atmosphere. So you start putting this junk in the atmosphere, and you're going to rapidly cause a rise in Earth's surface temperature that will be unsustainable. So these are the greenhouse gases that absorb heat and re-radiate it to the Earth's surface. What about gases that reflect energy back into space? Oh dear. Sorry about that, guys. Didn't mean to let that happen. Well, there's one, and that's sulfur dioxide. So sulfur dioxide is a fairly minor gas, but it's really good at reflecting heat back into space. And its major source on Earth is volcanic eruptions. So when Mount Pinatubo in the Philippines erupted some years ago, it put out so much sulfur dioxide that it cooled the Earth's temperature by about 0.5 degree. And that was pretty amazing. That spoke to exactly how powerful these gases are. The problem is that these gases are produced by human activity. Carbon dioxide, methane, ozone, nitrous oxide, and CFCs. These are all human generated gases, and they are building up in the atmosphere. They are increasing the rate at which heat from the Earth's surface is reabsorbed and re-reflected. So what is the effect of this? Well, all right. First off, there's a lot of debate about where CO2 comes from. You know, is it really human generated? Yes, it is. I'm going to show you the proof of that. So here's the historical record that shows you the relationship between mean surface temperature and atmospheric CO2 concentration. So I'm going to now move this back. All right. So here is the current day on the left, and here's 170,000 years ago. And the CO2 concentration is in blue. The temperature of the Earth is in red. Notice that you have relatively high temperatures when you have high CO2 concentrations. As CO2 concentrations fall, so does the Earth's temperature. This is an interglacial period. This is a glacial period. This is an interglacial. This is a glacial period. So here's the height of the last ice age. Okay. And notice that you don't have to have a huge change in temperature to flip us from a benign climate into an ice age, right? A couple of degrees centigrade is all it takes. Similarly, having this rise a couple of degrees centigrade beyond where we are now would put us back in Eocene level conditions where there were palm trees at the North Pole. So CO2 is the main driver of global temperature. Water vapor did not vary in this way. So even though there's a lot of it and it contributes half the greenhouse effect, water vapor does not drive global temperature. Carbon dioxide does. So let's examine now some of the direct and indirect pathways in which human activities do alter conditions on Earth. First off, human populations produce industry and they have agriculture, and these two activities are the main ones that are driving directly or indirectly changes in climate, in nitrogen, and in land use, which are the things that we're going to now talk about. So industrial activities directly put out CO2, agriculture directly puts out CO2, industry puts out nitrogen, industry converts land from natural cover to human use. Agriculture does the same. Agriculture uses nitrogen as fertilizer. But here's the thing. The changes in CO2 then directly affect global climate. But changes in nitrogen chemistry also indirectly affect the global climate. So industry has an indirect effect on climate by changing nitrogen. Agriculture has an indirect effect by changing nitrogen. Land use cover also has an indirect effect by removing plants that sequester CO2. And the loss of species that sequester CO2 changes the global climate. As climate changes, then you lose more biological diversity. So basically, we have a nexus of what we call wicked problems in problem-solving literature. So let's examine nitrogen and land use now that we've looked at CO2 and see how those processes are changing. All right, well, here's land use. Okay, so this is a photo of Rondônia State in Brazil from 1975. You see an unbroken expanse of tropical forest. The red is denser vegetation. The blue is less dense vegetation. In 1986, you see that there have been roads established, and there's significant deforestation. In 75, you have a small town here. It's become a city, and now it's a very large city. And you are losing incredible amounts of habitat now. And because this habitat is fragmented, we know that the principles of island biogeography apply, and we are losing species out of this habitat at really dramatic rate. Oops. And here's a summary of how those land use changes have affected the Amazon rainforest in general. So in 1978, you see that there's some development here. This brown is not strictly speaking rainforest. This brown is caatinga, which is a dry forest. And notice that there's a little bit of expansion here, but not much change in the dry forest. What's changed is the amount of development in the rainforest. It's particularly noticeable up here by Bahia. So human conversion of rainforest has been really spectacular up here. It's also been spectacular here and here. And this is the area from which that previous aerial photo was taken. So here you see how the basin-wide change in development of the Amazon rainforest is affecting the size of forest patches available. This is still huge, but look, it's not as huge as it was. We've definitely lost some species. This patch is much smaller. We've definitely lost a lot of species here. And the capacity for sequestering carbon has been significantly altered by these losses. Let's turn our attention to the third one. We're going to talk about climate. We're going to talk about nitrogen budget and land use. So nitrogen is the third one. So it's important to understand that the natural nitrogen budget has these sources. So lightning fixes nitrogen into the soil. Marine processes fix nitrogen. Some of the microbes in aquatic systems fix nitrogen into usable forms. And mostly it's bacteria in the terrestrial environment that does most of the nitrogen fixation. So this is teragrams. This is 10 to the 12th grams of nitrogen per year. And notice it's about 120 teragrams of nitrogen that are fixed by natural processes. And I want to point out that, get a load of this, human activities, the burning of fossil fuels, the use of nitrogen in industry and the release of nitrous oxide from industrial emissions, and the use of nitrogen as crop fertilizer has more than doubled the amount of nitrogen in the environment. All right, now we know something about what happens when you raise the availability of a limiting nutrient, right? Diversity crashes because the weeds take over. So the nitrogen requiring weeds are slowly driving everything else extinct because of our burning nitrogen, our addition of nitrogen into the environment. Now, it's important to understand the climate deniers. They are lying. And I will show you the evidence that CO2, in fact, is caused by human activity. It's incontrovertible. We did this. It's up to us to reverse it. So first, I want to show you the relationship between atmospheric CO2 and time. So atmospheric CO2 in the recent past, from 1000 AD to about 1750, was pretty constant. Okay, here we have ice cores that tell us that atmospheric CO2 concentrations started rising pretty fast, starting in about 1750. And then that trend has continued, and we have much, much finer detailed information from the observatory on Mauna Loa at the top of the volcano, which has been taking these measurements since about 1950. So you get a flat curve and then an exponential rise. Okay. The question is, where did this come from? Fossil fuel companies and those that make a ton of money from the fossil fuel industry say, well, it's just a natural cycle. No, this is due to the Industrial Revolution. We started this exponential rise in the Industrial Revolution, and look, it's going straight up now. Half of all the carbon emitted by humans in our entire history has been emitted in the last 30 years. Just remember that. So what can we determine about human activity and its relation to this carbon? Well, okay, so here's the temperature curve, right? And here is the emissions curve of CO2. And notice that we have some drops in CO2 due to World War I, due to the Depression, due to World War II. But other than that, it's been kind of a really good match to the temperature curve. Now, we don't have a huge amount of data on some of this, and there is a lag between the drop in CO2 and the drop in temperature, but it's a pretty close relationship. Now, here is the smoking gun. This tells us that, in fact, CO2 in the atmosphere is being put there almost exclusively by humans. Okay. This is the concentration of the C14 isotope in the atmosphere. So here's the relative concentration. This is higher concentrations of C14 relative to C12. This is lower concentrations. So when you have this, there's a lot of C14 out there and not as much C12. When you have this drop, it means that C12 is increasing and diluting the amount of C14. Well, now notice that this started on a downhill path about the time of the Industrial Revolution. So why would C12 start to increase in the atmosphere around the Industrial Revolution? Why would it be spiking so dramatically? The carbon that is going into the atmosphere is exclusively C12. It's because this carbon comes from fossil fuels. C12 is incorporated into plant tissues preferentially. C14 goes slower. The reactions go slower. So C12 is enriched in plant material. That means that if you're burning plant material, you're putting more C12 into the atmosphere, and the concentration of C14 drops. So the only source of C12 is fossil fuels that is large enough to account for this. So here is the drop in C14 concentration. And here is the output of industrial CO2. Notice that they are mirror images. As industrial output of CO2 increased, the concentration of C14 in the atmosphere crashed. That is because all of this carbon is C12 carbon. It's human fossil fuel burning. There's no doubt. Anyone who says differently is lying to you. Now, I think it's very important to know that we knew for certain that humans were responsible for almost all of the change in carbon in 1986. This paper was published on November 20th, 1986. I didn't see it until 1987 because I was a postdoc in Panama, kind of knee deep in rainforest mud when it came out. But when I did see it, I thought, oh shit, we need to do something about this. So it's very clear. There is no doubt. We are responsible. We did this. It is up to us to stop it. Now, the question is, of course, on everybody's mind. If we did it, can we do anything about this? Is it even possible? And this is where there's so much despair and so much denial. And I'm here to tell you that we can. We can do this. We know how to do this. And as an example, we're going to use the CFCs. Remember the CFCs that last for 50,000 years in the atmosphere? CFCs destroy ozone. Well, ozone absorbs ultraviolet radiation and makes the Earth's surface habitable. If we didn't have ozone, the Earth's surface would be blasted by the ultraviolet light and sterilized, and there would be no life left on Earth at all. So the accumulation of chlorofluorocarbons causing an ozone hole in the 1980s was cause for a lot of concern. Well, as a result of this, the nations of the world got together and instituted the Montreal Protocol, which got rid of CFCs. Now, even though they stay in the atmosphere for a very long time, look at what the effect of that was. So we had a growing ozone hole until the Montreal Protocol. We started ditching CFCs, and look, the ozone hole has turned around and is dropping. If we can do this with CFCs, we can do this with carbon. We can do it with methane, with carbon dioxide. We know how to do this. We can suck carbon from the atmosphere. We can go carbon neutral in our energy sources. We can reverse this climate change. The science is there. The political will is not, because rich people got rich by burning fossil fuels, and they don't want to stop. So it's your life against their fortune. That's, to put it bluntly, the stakes. So here is the fourth National Climate Assessment. And it was somewhat after the paper that demonstrated that humans were responsible for climate change. Okay, 32 years later. Well, here's what the climate assessment has to say. And the impacts of climate change are already being felt. I think we're aware of that since we have storms that have hit us, and parts of the US have been incinerated this year. In the absence of mitigation action, rising temperatures, sea level rise, and extreme events are expected to increasingly disrupt and damage infrastructure and make it difficult to continue to live. Future risks from climate change depend primarily on decisions made today. And yet, we have people who will not face facts. They stand in the way. They don't want us to go to an electric economy based on renewables. They don't want research into fusion power. They don't want reforestation. They want to continue exploiting as we've been doing. Well, we have the strategies in place to reverse climate change, to stop it in its tracks and reverse it. Global temperatures can be going down as early as 2040 or 2050 if we were to take aggressive action. We know what to do. We just don't have the political will. We have a small number of politicians who wield outsized influence, who are doing their best to see that these changes never happen. That will simply kill people in the future after the politicians are dead. So it's, go figure. It's future discounting, as economists say. Now, we have dithered for over 30 years. We've done nothing. And that means that we're going to lose South Louisiana. We're going to lose much of Florida to sea level rise. We're going to lose a lot of cropland, and we will have food shortages in the future, but we can still avoid a total meltdown of society. We have to find ways to cope with the things that we're going to lose, but we don't have to go extinct. The time is now. We are currently feeling the effects of carbon emissions from the 1970s. The effects of you driving to school today in a gasoline-powered car won't be felt until 2070. Expect that most of you will still be alive by then, so you'll feel the results of your own activities. But the point is that we know what we need to do. We need to find the courage to do it. And at that, I see that we're out of time. So I'm going to thank you for sticking with me this pretty horrible semester, and hope that you have a great break. I hope that you decide to take the exam and do well if you do decide to take the exam. And I'm going to be available all day today after I go get something to eat. And you know what? I'll be in on Monday and Tuesday as well. Remember, the exam is on Wednesday, December 8th at 10 a.m., 10 to 12. That's our time slot. I'll send an email out reminding you of that because I don't want you to miss it if you're planning on taking it. December 8th, 10 to 12. You already know a lot of what's on there. I will have more information if I can ever stop helping people with the laboratories. Okay, so do we have any questions before I end this and post it?
Yes, I have a question. For the final, what would you recommend to look over in terms of studying for it? Would you recommend the notes, lectures, just everything, or?
All right. So for the new material, it's going to be kind of a mini exam. It's going to be about half of as big as an exam as the normal hourly exams you've had, because we've had 4 topics. So there'll be some multiple choice and maybe 3 essay questions in the style that we've been having on these 4 lectures. So study for them the way you've been trying to study for the hourly exams. Make use of those study guides, big time. For the review section, the review is multiple choice questions that you have seen before. You might want to go back and look at the review at the previous exams and make sure that you understand why the multiple choice question answers are correct or incorrect, right? Because you'll see them again. For the extra credit, I'm going to take some big ideas, some big topics, and I'll ask you to write essay style questions, answers for them. You already know that I'm going to ask one on kind of host-parasite interactions. And I just have not even had time to think about putting any of the others together because my office has been pretty much continuously busy with people. And I do need to sleep every now and then. So for those, I would look at the big concepts. I would ignore the little things. And I would look at, what did Dr. Howard ask essay questions about on the hourly exams? Something that's important enough to ask an essay question on. Maybe that's a topic I need to review. Okay? That's how I would approach it.
Okay, thank
But
you.
I will have more information on the exact makeup of the final before we take that final. Okay? Anything
Okay.
else?
Do we need to, should we go over like the survivorship tables and everything and how to calculate that?
If I haven't decided whether to put a question like that on the extra credit, I will let you know if I think that you need to do stuff like that. There are other things in that part of the course that are kind of equally important, right? Like understanding population growth, like, so that's not a guarantee. I mean, I doubt that I would give you a life table to fill in. I don't think I do something like that. But on the other hand, you do need to understand the significance of like stable age distribution. You need to be able to identify a population that's going to grow at a constant rate versus one that's going to grow at a variable rate. So I don't think that a life table like fill in the blanks type problem would be in the cards for the final. I suppose if there was a popular wave of requests to do that, maybe I'd consider it. But,
Okay, thanks, Dr. Howard.
okay. Anything else before I shut off? All right, guys, come see me at 1 o'clock or after. We'll try to make the best of this rotten fall, and good luck.